All right. I was presented a problem from actually a former math teacher of mine way back in ninth grade when I took geometry with Mr. McCauley. Um, and the specific problem has to do with if I have four 8-sided dice. So I'm just going to make a square. I'm not going to bother trying to draw the three-dimensional version of an 8-sided dice. And each one of these dice has the numbers 4 through 11 and on it. And when you roll all four, you're going to sum them up. So the smallest number you can get in any case is 4, and there's 4 dice, so the smallest number you can get as a total is 16. The largest number on any one die is 11, so you roll all 4, the highest number you can get is 44. And the question was, what is the probability distribution? Meaning, what's a quick way of finding out what are your odds of, say, rolling a 27? Or quick is probably the wrong term, because as soon as it gets this complicated, it's only quick if you're using technology. But what are some strategies that we can use? What's a process? And so I was doing some thinking about it, and most of the things I was thinking of are pretty slow and labor intensive. And so, I do what I normally do when I come across, well, what have other people thought? So let's do a Google search. And the solution I found that most interesting to me involved polynomial expansion. And while it's still cumbersome, I mean, you're not going to solve a problem like this instantaneously. It actually is quite quick to do on a computer. In fact, Wolfram Alpha is perfect for this, so I'll show you how this works. But what I'm going to do is I'm going to pull back the problem, and instead of doing this exact one, let's just start with the most basic kind of problem. So let me erase all this here. Let's erase it. Okay, and let me start over. Let's see if I can get that going. Here we go. All right. So let's just say we had a two-sided two-sided die, and we just had one of them. Okay. All right. So two-sided die. Well, that's basically like a coin. But instead of saying heads and tails, we're going to say 1 and 2. Okay. So it's got a side that's 1, a side that's 2. And we're going to roll this multiple times, and we're just going to sum it up. And we want to determine the probability distribution. So let's just start with one roll. So you could get 1, 1, or 1, 2. And let's see if I can get the color scheme. What happened to my little color schemes going on here? That's weird. Oh, there's my color palette. So we've got 1, 1. There it is. And 1, 2. Okay. All right. Now, what if we roll it a second time? Well, there's one chance that I get 1 every time. So you could get a 1 and then a 1 and then a 2 then a 1, or 2 then a 2. There's 4 different outcomes. And so here we go. There's one way of getting 2 now, because we have 2 rolls. So one way of getting a 2. We have 2 ways of getting a 3. Okay, and we have 1 way of getting a 4. All right, now, again, this is two rolls of my two-sided die. So if I roll a 1 twice, I get 2. If I roll a 1 then a 2, I get 3. If I roll a 2 then a 1, I also get 3. So 2 ways to get a 3. And if I want 4, I've got to roll 2 twice. Okay. All right. Let's keep going. What if I'm going to roll it 3 times? What are the different options that are there? And I'm actually going to start expanding this quickly. And I'll go ahead and do 4 rolls. And why don't I do 5 rolls? And any student of algebra is going to notice, oh, whoops, undo that quite quickly, what I'm drawing here. Let's change the color. So what this would say here is that if I rolled it 3 times, so if I get 3 ones, that's a total of 3. I'm going to get 1 3. There's one chance out of that whole thing to get 3. There's only one way to do it, is to roll a 1 every time. But there are 3 ways to roll a 4. There are 3 ways to roll a 5. And there is 1 way to roll a 6, which is to roll a 2 every time. Okay, so again, we're in this scenario where we've got a coin that's 1 and 2, or 2-sided die. And we're just rolling and we're adding them up. And as we keep going here, down here there's 1 way to roll a 4, 4 ways to roll a 5, 6 ways to roll a 6, 4 ways to roll a 7, and 1 way to roll an 8. And just for good measure, I'm going to complete this here. If I roll it this 5 times, there's 1 way to roll a 5. There are 5 ways to roll a 6. There are 10 ways to roll a 7. And 10 ways to roll an 8. And 5 ways to roll a 9. And 1 way to roll a 10. And that's to roll a 2 all 5 times that you do that. And again, I said if you know algebra, you're going to recognize these numbers in blue here. This is called, if I put a 1 up on top, this is called Pascal's triangle. And it has this unique geometric property, I don't know if that's the right term, where if I, down the sides here is just the number 1. Okay, it's just, we're going to expand it there. But down the middle, all the middle numbers are just the sum of what's above it. So 1 plus 1 is 2, and 1 plus 2 is 3. 2 plus 1 is 3, 1 plus 3, 3 plus 3 is 6. Okay, and so it has that pattern of just adding down that direction, Pascal's triangle. And we use it for something called binomial expansion. Which means what happens when we can also, it's not the only thing we use it for, but one of the things we can use it for is binomial expansion. And the way it works is traditionally it looks like this. So if I have some number a, and I add it to some number b, and I want to raise it to some power n. Well, if the power of n is 0, I just get, if n is 0, my answer is 1. If n is 1, well, that's a plus b to the 1 power. That's itself. That's 1a plus 1b. If n is 2, so I'm squaring. Now I'm going to have to multiply a times b times a times b. Sorry, a times a plus b times a times a plus b. There we go. And to solve that, if I were to do it by hand, I'd have to distribute. And the first part would be a times a, or a squared, and then I'd get a times b. And then here I'd have b times a, which is the same as a times b. So I'm having that term twice. And then I have at the end b squared. And so I end up with 1a squared, okay, 2 ab's, and 1b squared. And so if I raise it to a power of 3, I get, I'm not going to do the whole triangle here, but I get 1a cubed, I get 3a squared b to the first, I get 3a to the first power b squareds, and I get 1b cubed, and the pattern can continue so on. And these all get added up as a total. Okay, so what does this have to do with rolling dice? How in the world did this expansion, and how can we use this principle then to answer my teacher's question? So let's actually go back to what distribution is. And I'm going to erase this, and we're going to start with a cubic polynomial, a pretty simple one, and we're going to multiply it by itself, and we're going to see what happens. Okay. So I'm going to take a polynomial, x to the first power. I'm going to write the 1 just for good measure here. X squared plus x cubed. So I'm just going to do a trinomial, 3 terms. And I'm going to multiply it by itself. So we're going to distribute, whenever we multiply one set of value, a polynomial times another, we need to multiply every bit, every term in one to every term in the other. So I'm going to have to multiply x to the first times every one of these. So x to the first times x to the first, well, that's x squared. Okay, x to the first times x squared is x cubed. X to the first times x cubed is x to the fourth. Okay, so I've done that. But then the next thing is as I actually have to do the same thing. Let me change the color so you can see this. I have to do the same thing here with x squared. I have to distribute it. I have to distribute again. So this is going to be multiplied. Okay, and so x squared times all those is basically the same list, but now just one higher power. So x cubed plus x to the fifth plus x to the sixth. And then I've got to do it one more time. I've got another distribution here. I'm going to multiply that by each one. And that's going to result in, wow, I totally messed up that last list. That is supposed to be a 4 and a 5. So let me fix that. I can count because I'm a math teacher, right? That's what we can do. All right, so x to the fourth plus x to the fifth plus x to the sixth. That's from taking x cubed here and multiplying it by each of those terms. So now I have this expansion here, and I'm going to combine like terms. Now notice that there are 9 terms because I had to multiply, I had to distribute each one. So this first one times 3 terms, the second one times 3 terms, this one times 3 terms. And the reason why this is important is because when you roll multiple dice, the number of possible outcomes is just a multiple. It's a power on the number of sides that die has. So if you roll a 6-sided die twice, there's 36 potential outcomes. 6 for the first roll times 6 for the next roll. And so this happens in distribution. I have these 9 terms. But just like when you roll dice, if you roll 2 dice, it's possible that you could have the same outcome generated, and then it happens more than one way. Basically, you have 2 things adding up to the same number. So if you roll 2 dice and you get a 1 and a 6, or you get a 4 and a 3, those both add up to 7, so your outcome's the same. The way you got there is different. Well, the same thing happens here, because when you multiply this by this, you're adding those exponents. But there's multiple ways that you can add up to each exponent number. For example, here's x to the fourth, which was x to the first times x cubed, so 1 plus 3. But over here I have x to the fourth, and it was x to the third times x to the first, so it was 3 plus 1. Well, here's x to the fourth as well, right in the middle. Well, that one was x squared times x squared, or 2 plus 2, so there was multiple ways. So basically, when I multiply a polynomial by itself, I am creating all of those. It's much like laying out the scenario. And now if I combine all the like terms, I can count up all the different ways each scenario is possible. So let me go ahead and do that. So let's combine these like terms. I'm just going to start with the lowest power. Here's x squared. Well, that's the only one. It's sitting there by itself. Okay, so I'm going to cross that off and let me know that I simplified it. Here's x cubed. How many of those do I find? I just find 2 of those. So there's 2x cubed. And then how many x to the fourth? 1, 2, 3. So plus 3x to the fourth. And then how many x to the fifth? There's 2 of those. I'm probably in the way now. Oh, no, not quite. Okay. And then 1x to the sixth. All right. That last bit of handwriting was not so great. X to the sixth. All right. Now, how does this relate to our problem? Basically, what this now is saying that if you had a 3-sided die, and you rolled it twice, a 3-sided die, and you rolled it twice, and the sides are 1, 2, 3, and you roll it twice, so you multiply it by itself. Okay. What it's saying is that when you roll one of those times, there's 1x squared. One of those times you'll get 2. You'll get 1 twice. 2 of those times you'll get a result of 3, a sum of 3. 3 of those times you'll get a sum of 4. 2 of those times you'll get a sum of 5. And 1 of those times you get a sum of 6, which is rolling a 3 twice. This is basically saying I have a 3-sided die that has the numbers 1, 2, and 3. I'm going to roll it twice, so that's what we're doing here. And then the resulting polynomial expression, the coefficient tells me how many times that particular result could happen. And then the exponent is what the result is. So one time, one way to get a 2. 2 ways to get a 3. 3 ways to get a 4. 2 ways to get a 5, and so on. So let's go ahead and go crazy here and go back to my teacher's question. And that was, what if I roll a 8-sided die where the lowest number is 4 and the highest number is 11, and I roll it 4 times? So how do we set that up? Okay, well, basically we just start with the x to the power, and the power represents the numbers on the die. So x to the 4th plus x to the 5th plus x to the 6th plus x to the 7th plus x to the 8th plus x to the 9th plus x to the 10th plus x to the 11th. And we raise that whole thing, so that's the numbers 4 through 11 on that die. We raise it to the number of rolls. We're going to roll it 4 times, or we're going to roll 4 die simultaneously. Same mathematics behind it. And we just need to multiply that thing by itself 4 times, which is possible to do by hand, but as you can imagine, just the first step, you're going to multiply 8 terms by 8 terms. That's 64 multiplication steps. And then you've got to combine those like terms, which is going to simplify it down to, I want to say off the top of my head, it's going to be like 15 terms or something like that. But then you're going to need to multiply that again by 8 more terms, so you're going to have like 120. The point being, it would take a long time. Not impossible to do by hand, but time consuming. So computers are really great at this. In fact, I've got an app on this device. All I do is type it in, hit enter. So I'm going to go over to that. It's called Wolfram Alpha. Which other way? Here we go. So I typed in the equation. I don't know if you can even read it up there. Unfortunately, I haven't found a way to zoom in on this here. And maybe I can find a way to make this bigger. No, it's going to be tough. Okay, so what I'm going to try to do is see if I can I copy that? No, I can't. Man, this is so tiny. Okay, I'm going to try to see what happens if I do this. I'm not going to be able to see it anymore. Okay, so I'm going to bring it up to the top where it says expanded form, and I don't know where I'm pointing because I can't see myself anymore. But I imagine it's somewhere up here. And it says x to the 44th, the result is x to the 44th, which means one time I would get a roll of 44. X to the 44th, 1x to the 44th. One time I get 44, which is something we knew at the beginning. You'd have to roll 11 all 4 times to get 44. There's 4 ways to get a 43. There are 10 ways to get a 42. And this is all from reading this expansion here. There are 20 ways to get a 41, 35 ways to get a 40, 56 ways to get a 39, and so on. It reads down the list. And so the most common roll here would be 344 ways to get a 30, which should be exactly halfway between 16 and 44. Yep. Okay. And so this polynomial expansion, which uses the distributive property, which has this way of combining like all these possible outcomes in a way that maybe it wasn't intuitive at first. What does polynomials have to do with rolling dice? But this is how mathematics, there's so many different approaches to solving these problems that sometimes patterns and processes that happen in one branch of mathematics can actually lay the foundation for a unique, novel, and optimal way of solving a problem in another branch. All right. Hopefully that made sense. Did to me. So yeah, that's one way. Polynomial expansion to figure out the probability distribution of any dice.